So hello everyone, and first I think I'll answer to because I'm not interested here. It's going to always going to come back here and see friends. And so this talk will be part 2 of the Daniel's talk yesterday. It's what we're thinking about Hartle-Hawking states, observers, parameters. And just to be clear that in this talk and closed universe will be safe and observers will also be safe and no one will be hurt. So I think since Daniel already gave his talk yesterday, let me just the background and motivation. I guess I could just basically just ignore it. It's just we learned a lot about ABS CFT and we learned a lot, let's say, about black holes. But the universe we ourselves live in may or may not have a spatial boundary, and in particular, it can be a closed universe. And by applying the lessons we learned from black holes, closed universe, we get a puzzling result that the fundamental universe space has mentioned as well. So let me just here lay out, let's say, 3 statements here. One is that there's only one closed universe state in any fixed holographic theory. I emphasize holographic theory, so this is the fundamental description. On the other hand, in familiar bulk theories, we can prepare many different closed universe states by path integral. And the third statement is that as we ourselves, as potential observers living in a closed universe, we actually experience rich semi-classical physics every day, and we observe standard quantum mechanics. I think it's passed various tests to very high accuracy. So let's first look at the statements 1 and 2. There's an issue of one stating fundamental description, but many states in effective description. And in the context of ABS, this problem was raised, let's say, decades ago by Marcina Maus, and this was related to factorization problem, or here what I mean, just how does wormhole emerge? Let's say what I mean is that in particular, let's say when you have 2 asymptotic boundaries, and there is a wormhole that connecting them, if you just look at a box solution, and after analytic continuation, you actually get the ABS closed universe. This is the Big Bang, Big branching, FRW, ABS closed universe. And the situation with the sitter is much worse, is that we don't know what kind of fundamental theories give rise to the sitter bulk. And actually, we don't even know if the fundamental theory itself is a quantum mechanical theory. And actually, holographic principle seems to imply that the fundamental theory just may not be quantum mechanics. And after all, quantum mechanics in one-dimensional Hilbert space is trivial. It's just a number. And what we will do is that in this talk, we'll simply assume the existence of effective description, and it's mapped to some fundamental descriptions. And we will briefly comment on its emergence at the end. I think as for the emergence of effective description in ABS case, it's related to factorization puzzle. I believe later talks, probably Hong or maybe Jonah, will make some comments on that. And let's say for the sitter case, we really have no clue, but let's assume its existence. So you may think that, let's say, if we assume that effective description exists, then we're all fine. Why do we worry about, why is there any problem with that? But it's not so, yeah, there's something sample there. It's, let's say, given statement, let's say 1 and 2, we assume that there are many states in effective description, but only one-dimensional quantum mechanics in fundamental description. And the third statement is that observers inside closed universe experience semi-classical physics. And the question we want to ask is that given statements 1 and 2, is statement 3 correct? It's actually not obvious at all. And the answer, what answer should we expect? The answer should better be yes, at least in certain contexts, like evaporating black hole. Let's say, for example, if you remember what Ami talked about yesterday, you say that evaporating black hole in fully observer probably just jumps to a closed universe. Or let's say the sitter space, if we ourselves live in one. And actually, for ADS closed universes, if we do the standard computation, the answer we get will be no, and I will review that later. And some proposed resolutions involves treating the observers differently. And the purpose of this talk is pretty simple. I just want to convince you that the theta is different from ADS. So, and here's the outline of my talk. At first, I will briefly review the problem caused by having one state. I'm not going to try to convince you that there's one state, but I will just show you that there are problems with that. And I will show you that why the theta, which I mean Euclidean sphere, is special. We look at it from the perspective both from perspective of both path integral and the holographic code. And of course, we want to ask about quantum mechanics. And in discussion part, I will comment on Boltzmann problem, and as I promised, I will comment on the origin, possible origin of the effective description, and the future direction consequences. So first, the problem of having one state. So though sounds rather surprising, having one state is actually the simple consequence of the holographic principle: zero area, zero entropy, and that's it. And I want to emphasize that it's one state in fundamental description, but there can be many states for effective description. And again, I'm not going to derive the example. And the statement that there's only one state follows from various path integral arguments. And in retrospect, it's actually just necessary if you want a completely evaporated black hole to be pure. And well, I want to emphasize that even if we assume there exists effective description with many different states, the problem caused by having only one state in fundamental description still shows up. And actually, it can make the space-time non-semi-classical. And roughly speaking, the underlying reason is that, I mean, we talk about alpha sectors, but different alpha sectors, they do not mix with each other. And this is actually necessary for black hole unitarity. And so for the problem, one way to see the problem is by doing some path integral computations. Let's say in particular, let's look at this problem in ADS closed universe. We will prepare a closed universe state, let's say by specifying certain Euclidean asymptotic boundary conditions. So what do we mean? What we mean is that once we have such a Euclidean asymptotic boundary, and for arbitrary closest slice, we can just compute the path integral that ending on this blue circle, blue slice, and asymptotic boundary. And this gives us a wave function. And when we have a wave function on all closed slices, we claim that we have a closed universe state. And in this particular context, actually, there is a saddle. The saddle, after analytic continuation, will give you this ADS embedding protein closed universe, as we discussed before. And the computation we will do here is that we'll consider expectation value of an operator O. And this thing we didn't discuss in previous paper. So this is a kind of special kind of boundary conditions. It's different from these asymptotic boundaries. For these asymptotic boundaries, I would require the manifold to end on these boundaries. And here I draw it in green. Let's say in this talk, whenever I talk about bulk operators, I will draw it in green. What we mean is that we will consider all manifolds that contain this. It's basically just you consider this as a bulk operator and you integrate over this operator over all possible locations. And we'll give more motivations about this later. And let's say in ADS case, let's say we try to consider, we compute the expectation value of this operator, and this is our boundary conditions of path integral. And just to comment on the notation that if we want to evaluate a path integral with certain boundary condition B, we will denote it by B bar. We put a bar once we try to evaluate. And in this case, when we evaluate this, I mean, this is, we like this answer. This is just gives us the expected answer in ADS closed universe. However, when we square it, that's where the problems come up. I mean, the first term we all like. And there are many other a few other cross connections. And I only draw one of them here, is that what if these two green circles all occur here? There are actually other cross connections. It's like this circle can be connected to this circle, or this circle can be connected to this circle. Just quite a few of them, depending on your assumption of CRT symmetry, this kind of things. And of course, there are higher order corrections. But the point is that these cross connections, they are comparable to the leading order terms. And just from topology counting, it's unless they are suppressed or managed for some very special reasons, they are actually comparable to the leading order term. I want to emphasize that here, there's one assumption is that the disk amplitude actually vanishes. It's once this assumption is not true, there are other subtleties, and Daniel talked about this yesterday. So with this computation and with this assumption, the problem is that these two are not equal, and the difference is very large, is actually basically order 1 corrections. And such wormhole corrections are familiar from black hole computations, but in those contexts, they are usually small, and they give rise to Page curve. And in current situation, the corrections are large. And in fact, it is exactly these large non-perturbative effects that manage to cut the theoretical space dimension all the way down to 1. And so far we see that there's a problem in ADS, and in ADS, there's a various proposals, let's say observer proposals to try to help with the problem. But now let's look at the Sitter case, and I want to say that the Sitter in this case, I mean, Euclidean sphere is different. So why the Sitter is different? First of all, it has no Euclidean asymptotic boundaries. This is clear. The Sitter is different, a sphere is different from cylinder. And there is another key assumption is that the partition function is large. The contribution to the path integral is large. It's actually, let's say in KT-like theories, there is a large topological factor, and more generally, we expect it both magnitude as the Sitter. And as a consequence, if you multiply two large numbers, the result is much larger than itself. I mean, this is basically all the mathematics we need in solving. And let's consider expectation value. Again, the same operator, but in Hartle-Hawking state. And we evaluate the path integral. And this is the expectation value of this operator. We just get, we have a sphere, and there is an operator inserted. Yeah, that's all fine. How about we square it? The first term, again, we all love. And the next order terms, you can have a couple of them, the corrections. Let's say, for example, you can put, let's say, both circles in the same sphere, or let's say you can change one of the spheres to a torus. But notice that in this case, all the corrections are actually subleading. They are suppressed by actually a very large factor, which is e to the minus s the Sitter. And so as a consequence, in this case, the fluctuation is not large, and these two are approximately equal. The wormhole corrections are small. And I should say that this was pointed out to us by Wang. So, I mean, when I first heard this, I was very surprised because I feel like, wow, there's the one state thing, so there's got to be some problem there. And how come the problem just doesn't show up in this case? And when you think about it just more carefully, you realize that, yes, one state conclusion still holds. And there are still large fluctuations for basically all other states, for generic states. But in this case, two conditions, no boundary and dominated by sphere, these two conditions are special. So we see that having no boundary is special. How about sphere? And actually, in retrospect, what I require, when I say that I need a sphere, all we require is that the partition function is very large. I think I had some implicit assumption that maybe hard topology things, the partition function cannot be that large, but if someone come up some theory with large partition functions with hard topology, I think that's also okay. But in this case, let's just focus on sphere. Let's say if you don't have a sphere, you have some higher topologies. Let's say this thing is of order 1 just by genus counting. And for order 1 number, the product of the two numbers is comparable to itself. That's again simple mathematics. And as a consequence, there will be large fluctuations. So sphere is special and the Sitter is special. And I cannot resist making some side comment that maybe it's not an accident that we actually live in the Sitter space. And I want to emphasize that it doesn't have to be eternal the Sitter. for example, for Coleman-Delucci bubble, it's the Euclidean saddle is also still have a sphere topology. All we need is really no boundary plus large action. That's a very small action, large partition function. And so, as I promised, we care about quantum mechanics. We talk about the experience of bulk observer. So what does a bulk observer see? Let's start from Hartle-Hawking state. And we condition on, let's say, we live in a universe that has an observer and an electron. And let's say X is an operator on the electron. And I will define a quantity like this. The right-hand side is path integral boundary conditions. As I showed you before, this is a path integral boundary condition that I will integrate a sum over all manifolds containing this, and the denominator is also something and a ratio of this too. And this quantity, I just define it as X and sub OB, and why I call it this way, it will be clear in the next slides. And if we want to evaluate this path integral, I think the standard way is to do replica trick, because once it involves ratio, it's tricky. And yeah, it's a full replica trick is needed. However, in this case, notice that because both the numerator and the denominator have small fluctuations as shown before, so they're self-averaging. And if we just want to know the leading order answer, then we just compute the first one, the numerator, and compute the denominator and take a ratio. And for that, you will get a good approximation up to corrections that are suppressed by, again, e to the minus s precision. And why do we give a notation like this? Because if you look at the saddle contribution, this saddle just, if we evaluate this saddle, it just gives the expectation value of this operator X in the center background with the observer present. And that is physical meaning, and that's why we just use this notation. And of course, we also wanted to not to receive large corrections. And in this case, there will be, say, one loop fluctuations, and hopefully they don't give us some extra minus sign or imaginary, certain power of imaginary parts, and I think there are various papers by one and Douglas and other people exploring this. I believe we will hear more talks on this later. Yeah, but here I assume that the one loop fluctuations is fine, and there will be non-perturbative corrections as we already saw, and these are suppressed by sphere partition function, which is very small. And there is some more technical thing is that the definition of operator this like this is a bit funny. Let's say one obvious technical obstacle is that let's say if we want to embed this into a torus, you can wrap it in many different ways, and that can cause a lot of trouble. And in fact, it's the definition of an operator like this is not physically very well motivated. The reason is that it seems like for this operator really specify everything on the spatial slice of the universe. And for any realistic observer living in the universe, we can actually only measure a small amount of things in part of the universe that's visible to us. So a more realistic definition of this is that, let's say, we just only condition on small amount of things. Let's say we condition that on the fact that observer is here, and there is electron here, and there is operator X on the electron. And let's say, I mean, this electron is dressed to the observer, and then in the path integral, we just integrate over this operator over the all possible manifold. And yeah, if you find, let's say, I can think of two motivations about this definition. One is just a string theory. When you define vertex operators, you always integrate the vertex operators over the entire string worksheet. The other thing is that I learned from Don, by working with Don, is that if you want to define gauge invariant operator in the Sitter space, you actually do some group averaging. Let's say this is observer state, this is the electron operator, and you have something like this. I would say that is analysis. So here is we just modify the definition slightly. Here's our new expectation value. This is this operator, and the denominator, I think, so far we could see that it just gives us an overall normalization factor. And when you evaluate that, we get the same result as before. It's the same saddle in this case. And of course, we also care about quantum fluctuations. It's better to have reasonable quantum fluctuations. And when we evaluate, let's say, x squared, we just put x squared here, that's fine. And if we want to look at expectation value and let's square it, we just put 2 copies of this here. And here is, again, the saddle. The leading saddle is what you want in actually, let's say, QFT in a current time. And these saddles give the expected value of quantum fluctuations of operator X on the zero background. And why do I talk about quantum fluctuations in particular? Because this is actually something that confused us for a long time. Notice that in particular, in this case, we get non-trivial quantum fluctuations. I would say that generic operators, that will be true. But this is not obvious at all, especially if you think about you have a one-dimensional Hilbert space, how come you get non-trivial quantum fluctuations? And this has to do with the choice of a careful definition of operators. Let's go back to see what we did. Let's say when we define the expectation value of operator X, we basically address the electron to this observer and we apply X. Let's say we measure the electron once. And when we define operator X squared, so one possible choice is just have 2 copies of this, but that's not what we do. What we do is that we say that one X measurement, another X measurement, we get X squared, then we address to this observer. And that's the key point here. So one way to say that is that we actually only have 1-point functions. I mean, when I say 1-point functions, I mean just a single entity here. But it can be 1-point functions of arbitrarily complicated operators. What I mean is that this operator X can be a product of arbitrary number of simple operators on the electron. If we want to first measure spin in one direction, spin in the other direction, we just multiply these operators, and then we address that operator to the observer. So what do we mean? I mean, as we said, the goal is that we want quantum mechanics. So the thing is that once we have all possible correlations on these electrons like this, a Hilbert space actually follows by GNS construction. And in this sense, the quantum mechanics of the electron emerges. And as an example, let's talk about transition amplitude of electron from 2s state to 1s state. Okay, I know that we need a hydrogen atom for that, but let's say, and the transition amplitude will be computed by correlators of form like this, where the first operator creates the electron in 2s state, and the second operator annihilates the electron in 1s state. It's a 1-point function of a product of operators. And since in this case, the quantum mechanics is emergent, a natural question is that how good is this emergent quantum mechanics? And we've already seen that again that there are non-perturbative corrections, let's say suppressed by e to the minus s de theta, and this is okay. I mean, this basically says that this tiny kind of things is that even if I give you all the degrees of freedom in the universe, you won't be able to have the capacity to measure that. But the dangerous things are the perturbative corrections of order G Newton due to the fact that we address everything to the observer. And imagine that observer may squiggle around and that may cause problem. And for this, these operators need to be carefully defined to preserve the operator algebra of the electron. I mean, we might need to do it order by order in G Newton, carefully, yeah. And how about from the perspective of a holographic code? So Daniel talked about the code yesterday. So here I will just briefly mention that we assume the existence of bulk theory, which is effective description, and we assume that there's a map to the fundamental description. And all of this can be actually characterized in the language of a holographic code. It's like there's one state in effective description, just mapped to the fundamental description by, let's say, orthogonal matrix O, and in this case, it is just a number. And note that this code is highly non-isometric. Everything is mapped to a number. It's because we have one-dimensional Hilbert space. And it's known that averaging over simple quantum codes actually reproduce path integral calculations to very good accuracy.
In what follows, I will just use the simplest possible code, basically just a single matrix, single orthogonal matrix O, let's say acting on a particular state. And I think in Daniel's talk yesterday, he showed you a more structured code that gives better match of gravity. But for conceptual clarity, I mean, in this talk, I'll just use a simple code. The map is pretty simple. Is that you have a path integral objects, and this thing is like, let's say, how do we define these objects? We condition on existence of this observer and the electron, and then we apply the operator to the electron. So let's say in some Hartle-Hawking state, we do some projection, then we apply X, and that's all. And if we evaluate this particular code by performing a Hartle integral, this is what we obtain. And the leading order answer is normalized trace. And the subleading order is suppressed by 1 over D, where D is the rank of this matrix. Roughly speaking, is number of effective states you have. So it's again e to the s de theta. And again, we want to look at quantum fluctuations. Let's say this is x squared. You replace this by x squared. And if you take the expectation value square, then we just have 2 copies of this. And after Hartle integral, this is what you get. This is basically more or less expected from standard quantum mechanics answer. Notice that, so here we obtained a normalized trace. I think Daniel obtained something yesterday which has a better match with the gravity. But exactly what you get depends on the detailed structure of the code, and which code is nature using, I mean, we don't know. But here, I just want to emphasize that whatever code you use, in this case, it gives a standard quantum mechanics answer up to small corrections. And this is non-trivial, because this is not true in ADS case. And just for completeness, I can briefly tell you that what's the technical reason that it fails in ADS from the code perspective. From the code perspective, if we look at that, if we don't do Hartle average, then all we have is standard quantum mechanics. It's true in ADS case, it's true in DS case. However, the difference is that for DS case, we assume that this thing is non-vanishing, is order 1. It's at least it's not extremely small. So let's say when we perform a Hartle integral like this, there's a leading order answer, which is just take basically this value over this value. And then there is other, let's say we can contract this O with this O, or this O with this O, but all those are subleading. And for the earlier ADS case, in order to get this crunching ADS cosmology, we need 2 asymptotic boundaries to connect together. And mathematically, what that requires is that the leading order answer was already given by connections by, let's say, this O with this O, this O with this O. And when you square it, there are different ways to connecting them, and that's what gives you large corrections. So, of course, as I emphasize again and again, the really difficult problem is where does effective description come from, and where does this code come from? And we don't know. We'll just make some comments later. And so after, let's say, I show you that the theta is different, but there are some caveats that I want to comment on. The first one is the Bohr's membrane problem. So in order to talk about Bohr's membrane problem, we want to ask the question is that whose quantum mechanics? I claim that we see a quantum mechanics emerge to a very high accuracy, let's say suppressed by e to the minus s de theta. But this is a quantum mechanics governing the electron, not the observer. And this construction follows the idea that in order to have quantum mechanics, one actually needs a classical observer. And I learned this from Daniel, and yeah, it's I think the rule of in this paper, observer rule in this paper was also motivated by that. And yeah, as we all know that Daniel likes to say crazy things, so we need a classical observer to have quantum mechanics. And but in this case, someone said this earlier than him. That's Bohr. So this is from I think the idea was advocated by Bohr, and this is just from some of his correspondence with Einstein. And I was also told that it's emphasized by Landau in his quantum mechanics book. So in particular, the quantum mechanics we obtained here I want to emphasize that, is not a quantum mechanics on the third quantized Hilbert space. So it is not baby universe quantum mechanics. We didn't obtain baby universe quantum mechanics. And in fact, if you have a de Sitter and you look at electron itself may not be gauge, it doesn't even satisfy the gauge constraint. I mean, to satisfy the gauge constraint, you need to have observers and other things there. But my question is that, do we have or do we need a baby universe quantum mechanics? So, I mean, this is related to the issue of Boltzmann brane problem. And here is a very extreme version of Boltzmann brane problem, is that if we consider transition amplitudes between two different states, two different slices, and yeah, if we consider if we consider transition amplitude between two different slices, and if we just do path integral, and here's what we get. This is a leading order term. This is the next order term. And unless this thing is exponentially suppressed, this term generically is much larger than this term. So the dominant contribution actually comes from, let's say, this first term. What this first term tells us is that the entire universe just disappears and reappears by fluctuation. And in fact, as Daniel emphasized yesterday, if we just compute transition amplitude between properly normalized states, we always get one. I mean, this is expected. You have one-dimensional quantum mechanics, all states are the same, so transition amplitude is always one. And is this a problem? So my perspective is that we only talk about transition amplitude when we have a quantum mechanics ecosystem, and we have quantum mechanics when we have an observer. And in this case, there is no reason for the entire universe to be a quantum mechanical system. For example, whose quantum mechanics? I mean, it can only be some super observer. So what do I mean by super observer? When I say super observer, I mean that someone can sit there and see different universes plopping, let's say, just appear, then disappear, just definitely someone outside the universe and can see all the universes around himself. And so I want to say that this particular version of Boltzmann problem is a problem for a super observer trying to do quantum mechanics. And actually the answer we get is expected because he has a one-dimensional quantum mechanics. And so one thing we want to point out is that in string worldsheet theory, we actually do have a super observer, which is the observer living in the target space. And so frequently when we talk about this one-state issue, people would ask us, well, in string worldsheet theory, you also sum over topologies, and why that in that case, you don't have the issue of one-dimensional Hilbert space. I think the technical reason is that the rule is different, and Daniel talked about it yesterday. And for me, the conceptual reason is that in string theory, we do have a super observer because that's us. We live in target space and we watch all those particles and we see quantum mechanics. While for the universe, it's not clear that if it's someone sitting outside the universe and watching all the universe surrounding him. And in fact, the entire closed universe does not need to be a quantum mechanical system. In retrospect, I mean, Lenny emphasized to me about this years ago, but I didn't appreciate that. So how about, let's say, transition amplitude seen by observer sitting in a universe, I mean us. What about transition amplitude we see? So I don't think we can specify everything on the slice, but what we can do is to specify certain information on part of slice, then we trace out the rest. And here's the path integral evaluation. And in this case, the boundary conditions is actually a slit. And this is like a particular kind of one-patch operator we discussed before. So, okay, I have 2 minutes left. So the origin of effective description, that's the hard part. So when doing path integral computations, we assume the existence of bulk theory with well-defined path integral. When we're doing code computation, we assume existence of code. But the question is that what fundamental descriptions can give us such an effective description or such a code? Here, I just want to list two possibilities. One possibility was emphasized by Daniel yesterday is that maybe we have something similar to ADS-CFT. For example, string theory may contain de Sitter vacuum, and such a theory will have both closed universe and open universes. And for this, the fundamental theory probably will have to have some quantum mechanical. 1 minute. Yeah, and the fundamental theory will have some quantum mechanical structure. But there are challenges. First of all, looking for such vacuum is very challenging, and there are some recent progress. And we also don't know what the fundamental theory is. The other issue is that when a theory contains both, when the landscape contains both open universes and closed universes, there can be issues with one-point functions, as Daniel mentioned in his talk yesterday. And another possibility is that what if we just give up the quantum mechanics in fundamental description? And one feature is that if you don't have a quantum mechanics in fundamental description, probably such a theory incorporates closed universe, but may not be open universe, definitely not ADS, like asymptotic ADS open universes. So is it good or bad? I don't know. You can decide yourself. I personally find it will be fun. And so what we may have an ensemble average of alpha sectors that can span the entire effective description. And we will also need some map from some operator algebra to random numbers. Let me elaborate it a little bit more. What I mean is that if we look at the computation we did before, the expectation value of these operators, from the perspective of path integral, there is an operator, and this is actually operator on the third quantized Hilbert space. And in each alpha sector, we just get a random number. We use this O to O of alpha to denote this number. And in the code description, what we did is that there is a Hartle-Hawking state, and we do condition P, we do evaluate the expectation value X. Yeah, and so this is the triangle close. And when we evaluate a path integral or we evaluate the code, so what we do is that we just integrate. When we integrate over O, we integrate over alpha sectors here. And here, one thing I want to emphasize that I think actually Lenny has been advocating for years that for a theory of a closed universe, in de Sitter in particular, all you have are just the correlation functions. It's like one state, then do projection correlation functions. And he wants to say that all the physics is encoded in these collections of correlation functions. And again, I didn't understand that until I understand it myself. That's always the case. It's now we see that this emerges. And but of course, the really difficult question is that, yeah, from this we can get this, but how about going in other direction? That doesn't sound to be easy, and that actually doesn't sound to be possible. There must be something missing. There will be some ingredients missing. And another challenge in Daniel's talk is that are these alpha states well defined in higher dimensions at all? I mean, I actually believe that Hong will also probably mention something like that. These things may not exist. Path integral may not be well defined in higher dimensions. So as for future directions, I mean, this topic is incredibly confusing. We know very little, so it's just randomly list something. Of course, this is the most difficult problem, the emergence of effective description. And the de Sitter static patch. We already see that sphere is different, de Sitter is different. The static patch, maybe there will be more surprise for us. And more phenomenology is like initial conditions of universe. I mean, we only see that in principle, quantum mechanics emerges, but how about which state are we in? Let's say, of course, we want to incorporate slow roll inflation. And there's a question that emphasized by Wang multiple times is that is Hartle-Hawking state phenomenologically viable? And in this case, in my talk, I only look at one very extreme version of a Boltzmann brain problem. And I want to argue that that's not a problem, but how about other versions of Boltzmann problem? And that's all I have. Thank you.
Thank you for the nice talk.
Yeah.
I have a question about your point that only a super observer needs can probe the maybe universe hyperspace quantum mechanics.
Yeah.
So I think that from the point of view of an observer, you can think of in the bulk, you can think of some geometrical operator that is non-diagonal in the alpha sector.
Actually, I find that that's a pretty dangerous thing to do because just following Coleman's, the thing is that if you can mix different alphas as observer, and then you may lose unitarity, and just because Coleman's argument will fail if you manage to mix alpha.
Right. If as I agree. If you want to recover something like the phase curve, and so you are measuring some boundary quantity in some open universe state, then I agree that those are super selected in alpha. But that you can define bulk geometrical observables, for example, that mix alpha sectors. So in that case, isn't it possible that possibly a bulk observer could probe the quantum mechanics of the baby universe with respect?
What do you mean by probe quantum mechanics? The bulk observer doesn't see universes pop up and disappear. And the bulk observer see how the electron appears. So it's, I'm not sure if the bulk observer should have operators that would change different alpha. I highly doubt that. But I just think that the entire universe as a quantum mechanical system does not have operational meaning for the observer.
Right. Okay, we can talk more about that.
So very nice talk. So I'm curious how you're distinguishing between de Sitter and ADS. So you've made a very nice point that there's a mathematical difference.
Mathematical difference, but in this case, it actually changes the story. It's in the sense that in ADS case, if you have this particular type of ADS crunching closed universe, you need a different asymptotic boundary connecting together, and that gives a problem of large fluctuations. Well, this problem doesn't occur in de Sitter for two reasons: no asymptotic boundary, large partition function.
My question is, how are you distinguishing that? Because for instance, in string theory, of course, the cosmological constant is not a parameter of the theory. It's set dynamically as the vacuum energy of some application. Once you're down to 0 dimensions, the wave function spreads over the entire string landscape in principle.
Okay, you ask me that what's the rule? Let's say if we have a landscape that contains both closed universe and open universe.
Or closed de Sitter and closed ADS.
Closed de Sitter, then closed ADS. Okay, then that's more related to what Daniel talked about yesterday. I mean, one simple answer I can give is that first of all, it's up to you that if you really, let's say, you want to recover the semi-classical physics as in ADS part, and if you want to do that, you can use various observer rules. And you can also apply the observer rules to the de Sitter part. It just doesn't do much. It basically doesn't change the answer.
Does your results rely on not doing multi-spheres when you're, or what is the principle for ruling out multi-sphere contributions that naively dominate?
What do you mean multi-sphere contribution? Let's say
The sphere has one, it has e to the s or partition function, but two spheres has.
Yes, I think
if you look at that, this has to do with the fact that we emphasize that we only consider 1-point function.
No, but I mean, in the 1-point function, you could include.
You mean other vacuum bubbles?
Yeah, just many.
Oh, yeah, I see. Vacuum bubbles will cancel out. And I think Daniel mentioned that yesterday, and it cancels out for good reasons, because the vacuum bubble actually has to do with the fact that because of vacuum bubble, you would say that Hartle-Hawking state is now normalized. So that has to do with the fact that this alpha probability distribution is now normalized. If you normalize that, you just automatically ignore all vacuum bubbles. This is some technical thing that I learned. I'm happy to explain later. Yeah, but the thing that vacuum bubble, just always ignore that. Yeah.
Why isn't there? Well, let me put it this way. You're changing quantum mechanics, and I think.
I'm not changing quantum mechanics.
Well, you just said that you need to introduce a classical observer. You reminded us of the Heisenberg cut.
Yeah, but I think
The point is that with the classical observer, you see, okay.
That's limiting the regime of quantum mechanics,
Okay.
and that's difficult, right? You have to come up with a new theory that still, lets physics have a unified description of nature. That was the problem with the Heisenberg cut. For example, why doesn't the observer radiate an infinite amount of heat? I mean, there's a reason quantum mechanics was invented. I feel like these are difficult problems and we should be thinking about them, but this sort of jumping to this conclusion that we just get to, introduce a parameter as observer that we have no prescription for how to measure it, and it's fundamental to the theory. It seems really dangerous to me.
First of all, you might talk.
As observer never came up, and the second thing is that I want to say that the rule is to recover the quantum mechanics with C, and actually, as I mentioned, I mean this idea was already proposed by Bohr, and I don't think he wants to change quantum mechanics. He wants to explain quantum mechanics that conceptually such thing exists because you have a classical observer. And question that I asked multiple people and no one gave me a good answer is that let's say if there is some superpower agency, whatever, that can do arbitrary operations on me and put me in arbitrarily weird superpositions, well, I conclude that Copenhagen rule still works. I'm not sure. Yeah.
Okay, one more question.
Can you go to your slide towards the end with the triangles on it?
Triangle.
That one, yeah.
Yes.
Zero is a state in a one-dimensional Hilbert space?
No, zero is a state in
Effective description, and it's this thing is in effective description. Let's say so. The left-hand side, this is object in path integral, and this is object in effective description of the code. And I mean, after you evaluate that, take the expectation value. Let's say you get yeah.
So like OPXPOT, like that's an algebra.
Yes,
that's an operator
yes.
in
That's what I mean is that we need a map from an operator algebra to.
Right, but it's the operator algebra of a gravitational theory and like QFT in curved space.
I don't know. I mean,
Presumably that emerges from some more fundamental way. Actually, one reason I can point out here that one reason why do I like the idea of alpha is because that, let's say if you cut this open here, you need something to expand this. And one idea, very naive idea is that maybe alpha can expand that. But I don't know, yeah.
Okay, one more question.
Yeah, I didn't quite understand your definition of O. Is O an operator that acts on the maybe universal Hilbert space? Can I think about it that way?
yes, and actually,
Daniel had some argument to say that O is basically generalizations of Morph-Max field Z, is that they actually all commute with each other. It's just the integrate over everything.
That contradicts what
There's
there's
two O's.
Now there's O, now there's O.
In the first slide.
The first O, yeah.
Yeah, the first.
Yeah.
But I don't quite understand that O, if it was really a generalization of the Morph and max field Z's, it would only be connected to a space-time on one side.
Oh, they only connect to space.
Oh, yeah.
Okay, when I say generalization, I mean that it takes the specific values in alpha sectors. But the rule is that you integrate over, let's say, all possible such things. Let's say you embed such things in a space-time manifold, and you sum over all possible manifolds with all possible ways of embedding that.
But I think your O doesn't commute with Z's anymore then. I think it does.
It does. It gives a number. It's you can first put O there. It's like a part of boundary condition. A path integral.
Can first put Z or then put O, or first put O and put Z. It's yeah.
Maybe we can discuss
Yeah,
afterwards,
yeah.
but I'm not sure though.
Yeah.
All right, let's thank Ying again.